Hi guys, welcome to the lesson of partial differential equations. So we are discussing the heat equation. We have discussed about various forms of heat equation with homogeneous, non-homogeneous, time dependent and time independent conditions. And we saw that every method has some restrictions, and that's why we are trying out some other methods. So in this class, we are going to talk about the method of eigenfunction expansion. That is a very amazing stuff. And we will see that how we are going to carry out problems using this method, right? So the idea is a heat equation is given, and you can see that it is a non-homogeneous heat equation with the homogeneous boundary conditions, right? So on the right hand side, we can see that there is a function of x and t that is a heat source. This is called heat source, right? So this is a heat source applied at the on the rod, let's say, and then the behavior going to see the behavior of heat, right? So the initial condition is given as u naught of x. So some function of x, maybe any function. Therefore, these are the Dirichlet, homogeneous Dirichlet boundary conditions we can see here. So for these conditions, we are going to work out, right? So now before starting the method of eigenfunction expansion, we are going to recap what we learned in the previous lessons, because that is going to help us here, right? So the solution for this problem, we learned that we start from assuming that u of x comma t is equals to some function of x and some function of t, right? And then we calculate eigenvalues for the problem, and then we generate journal solution. So here we can see that the journal solution that we generate is in this form: tn of t, xn of t, x, sorry, it's not t, this is x, right? So xn of x, right? Where xn of x are the eigenfunctions. These are the eigenfunctions we calculated in the previous lessons for three cases, that is lambda greater than 0, equals to 0, and less than 0. So the idea is to decompose the function of xt into components, and we can say that f of xt is equals to f1t times x1x, then f2t times x2x, and then through fnt times xnx, right? So we are going to find the response. Then un of x comma t is equals to tn of t, xn of x. So the steps for this problem are: find the function xn x satisfying the conditions. For example, if these are the boundary conditions, that is homogeneous Dirichlet conditions, then we know that x of 0 is 0 from here, x of l is 0, and it gives the eigenvalue only for the third case, that is lambda less than 0, right? And we get this eigenfunction for that corresponding eigenvalue. So this is our eigenfunction, and we are going to expand the solution using this function. Then step 2 is find the function fnt. So from here, in the previous step, we called it as f1 of t times x1 of x, f plus f2 of t times x2 of x, and dot dot to fn of t and xn of x. Therefore, for x1, we substituted sine pi x over L, because we called that the eigenfunction is equals to sine n pi x over L. Therefore, we generated the series for corresponding n, and for n is equals to 1, 2, 3, dot 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 to n, right? So now to find fn of t, we are going to integrate the function of x comma t with sine n pi x over L using the Fourier series. So we will integrate this function whatever the function heat source is given, this is called heat source. We already discussed that earlier. This is called heat source. So whatever the heat source is given, we are going to integrate the source with the sine n pi x over L, limits from 0 to L, right? So this is the idea of Fourier series. All right, so now this sigma n is equals to 1 to infinity, and this, you can see that this is now a first order differential equation that we will discuss how this equation is formed, times this sine pi x over L is equals to sigma n 1 to infinity fn of t sine n pi x over L. Now from here we are going to generate the family of ordinary differential equations. Then we need to find the initial conditions, and then we will solve these families of ordinary differential equations to find the general solution for the problem, right? So in order to solve this family of first order ODEs, we need initial conditions. So for initial conditions, we will move to step 3, and the ODEs will be given by this equation, right? This will be the equation. So for A1, it will be A1 prime plus K pi square over L. A1 is equals to F1. And for A2, it will be A2 prime plus K 2 squared pi squared over L times AN. This is L squared, in fact, right? So like that. And for in step 3, now we are going to find initial conditions using the given initial condition in the problem, that is ux comma 0 is equals to u naught of x. So u of x comma 0 is equals to sigma n 1 to infinity n of 0 sine n pi x over L is equals to u naught of x. And then again we are going to integrate as we did in the Fourier series, Fourier sine series, and from here we are going to find the initial conditions. Then we can see that we will find this equation, and we, in fact, we already found this equation, but we are going to find these conditions, right? These are the initial conditions. So let's move to an example. Here a problem is given, a heat source is given. We can see that this is a function of x and t. All right, and the conditions are perfect. There are homogeneous regular boundary conditions, and we need uh, always homogeneous conditions for this eigenfunction expansion, right? So the very suitable condition for this method is the homogeneous boundary conditions. If the conditions are given are not non-homogeneous, then we are going to convert the conditions into homogeneous, and we already learned in the previous lessons how to do that, right? So here function of xt is equals to this. This is function of xt, and the first step is to integrate this function with sine n pi x over L. So L is given as 1. Here we can see that L is equals to 1. All right, so we will integrate the function, and we know that here t will be treated as constant because we are integrating with respect to dx. So the integral of sine pi x and sine pi x, we will use the condition of orthogonality, and we know that for when n is equals to m in this case, then we get the answer, the integral 1, right? So the value of this integral will be 1, and when n is not equals to m, then this integral is equals to 0, right? Implies 0. So for sine pi x and pi x, we will get the value for n is equals to 1. So it will be, sorry, it's not 1. In fact, it's half, right? So we will get t for n is equals to 1, and we will get 0 other than 1, right? So here we can see that it's sine pi x, sine n pi x dot sine n pi x is equals to half for n is equals to m, and 0 for n not equals to m. So here f1, we can see that now f1 is equals to t, because we can see that at n is equals to 1, this is t. So this means that this is f1, and for any other n, like f2, f3, f2, fn, we will get 0, right? So f1 is equals to t and all other f's are 0. Now we are going to talk about the initial conditions. For initial condition, as we told that we have to use the initial condition ux comma 0, and we have to integrate with the function of sine, because we are using the sine expansion, and we know that for Dirichlet boundary conditions we always use sine expansion, right? So u of x comma 0 is equals to 1 in this problem. Therefore, we are going to integrate sine and pi x with the product of 1 dx, then we will get this function here, right? So this implies 4 over n pi when n is odd and 0 when n is even, right? So here we are going to construct the family of differential equation with the conditions. So here, now we can write, for this n, we can write to n plus 1, because we are saying that for n odd, we are going to have this value 4 over n pi. Therefore, we can write n is equals to 2n plus 1, right? Or we can leave it as it is. It doesn't matter, right? So here we said that 2 times n, that is when n is prime even, so all values will be 0, and a2n plus 1, that is when n is odd, then we have this value 4 over 2n plus 1 times pi. Therefore, a1 is equals to 4 over pi when n is 0, when n is 0. So here is a1, and when n is equals to 1, here is 4 over 3 pi, and when n is equals to 2, and so on, right? So here k is equals to 1 in this equation. Therefore, we are going to generate the family of ODEs. So first of all, we are generating for evens, that is a prime to n. Using this equation, we know that a n prime k n squared pi squared over l squared times a n is equals to f n, right? So this is the formula for the family of ODEs, and we are going to use this formula for defining the evens and odds separately, right? This will ease our problem. Here we have generated for n is equals to 2n, because we are dealing with evens here. So we know that all f's are equals to 0 for evens. So here all these will be 0. So this equation is 0 and the condition is also 0. Therefore, these all prime even ans will be 0, right? So this equation will always give a2 is equals to a4 is equals to a6 is equals to dot 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 0, right? And now we are going to use for odds. Therefore, we have written as a prime 2n plus 1 plus 2n plus 1 squared pi squared a2n plus 1 is equals to f2n plus 1. So here the condition we already formulated, that is a2n plus 1 of 0 is equals to 4 over 2n pi, or 2n plus 1 pi, right? So for a1, for n1, that is a1, f1, we know that f1 is equals to t, and all other f's, that is f3, f5, and f7, that are equals to 0. So we are going to treat f1 separately and these all separately, right? So here we can see that a2n plus 1 prime and 2n plus 1 squared and this. So we are going to equate here. We will see that. So equation 1 is easy to solve, and we already discussed that this will be equals to 0. And for equation 2, we are going to split this equation for a1 prime plus pi squared a1 is equals to t. Therefore, and the initial condition will be 4 over pi because the condition is 4 over 2n plus 1 pi. And when we will put n is equals to 0 here for here 2n plus 1, then we will get a1, right? Because here is a2n plus 1. So we need a1 because f1 is equals to t. So we are going to treat this separately. Therefore, we have written this separately. We will solve this equation. We have the initial condition, we have the equation, we will solve the equation. This is the first order ODE. In fact, it's a linear first order ODE, so we are going to use the integrating factor to find the solution of this differential equation. And here you can see that integrating factor is equals to pi squared t. Then we multiply the equation by integrating factor. Now this left hand side is exact, and we will solve here, right? So then also this is written directly, but we also applied the initial conditions. I assume that you guys will do that easily because this is very basic stuff, right? So after finding the solutions to this equation, apply this condition and you will get this answer, right? Here's the answer. And now for a2n plus 1, right? We already talked about this, that all other f's, odd f's other than f1 are 0, right? So we are going to treat this separately, right? A2n plus 1 prime plus pi squared a2n 2n plus 1 squared a2n plus 1 is equals to 0. And then we will solve this problem and we will apply this condition, this initial condition. We will get the solution here. A2n plus 1 is equals to 4 over 2n plus 1 times pi e to the power negative 2n plus 1 whole squared pi squared t. So now the final solution is this one that we talked about in the initial steps. Right, so we have formulated an of t, and now we will write here the an of t with a sine n pi x. So this an of t is for n is equals to 1. Therefore, this will be with sine pi x. And then all this stuff is for all other n's, and in fact, all other odd n's, because here it is 2n plus 1. This means that we are talking about odd ends, right? Odd numbers. So this is the general solution to this equation using the method of eigenfunction expansion. And this is very really amazing stuff. You can see that how we are approaching the problems in a beautiful way and beautiful steps and very great ideas. All right, so now we will talk about some more problems. Here we can see that this is ut minus k uxx is equals to sine t. And ut minus k uxx is equals to sine t, and the boundary conditions are again the Dirichlet conditions, and we can see here the initial condition is given 0. So it will make our work easier. Here we will apply the same method for eigenfunction expansions. The solution is given by uxt is equals to summation n1 to infinity a n t sine n x. So we have to find this a n xt, right? So sine nx, because of this sine n pi x over L. And here L is equals to pi, therefore the eigen function is sine x, right? Sine nx. Now fn is equals to 2 over pi 0 to pi, the function of xt with sine nx. Function of xt is given as sine t. Therefore, it's a function of t and it can be moved out of the integral. It will be treated as constant and we will integrate sine nx. The integral is negative cosine nx over n. Apply the limits, so we'll get this form, right? So fn is equals to 4 over n pi times sine t for n is equals to odd, and for n is equals to even, this will be 0. And again, an of 0 will be 0 because the initial condition is 0, so no need to find this an. It's 0, the initial condition. Here we can see that it's 0. So the ODE becomes an prime plus kn squared. An is equals to 4 over n pi sine t. And we have to find this only for the odds, because even ones are 0 and the initial condition is also 0. So for a2n will be 0 again. And we only need to find an prime, right? So we can also use n is equals to 2n plus 1 here, but we are going to use n. It's fine. It doesn't matter at all. All right, so an prime plus kn square n is equals to 4 over n pi sine t, and an of 0 is 0. We'll solve this equation. This is first order ordinary differential equation. In fact, it's a linear ODE. We'll find the integrating factor and we will solve this ODE, or we can solve it by using the auxiliary equation and work out for homogeneous solution and then work out for the particular solution, that is for sine t, right? So here is the idea. An is equals to an homogeneous plus an particular. So for homogeneous, the auxiliary equation will be r plus kn squared is equals to 0. This will give r is equals to negative kn squared. The solution will be an homogeneous is equals to c1 e to the power negative kn squared t. Now we'll find the particular solution. For finding particular solution, we are going to use the method of undetermined coefficients. This is undetermined coefficient. We are familiar with this method. We have done in finding the solution for second order ODEs, undetermined coefficient method, right? So this is undetermined coefficient. So a and p is equals to a cosine t plus b sine t. Then a and prime is equals to negative a sine t plus b cos t. We will substitute this into the original ODE. Then we will compare the coefficients by arranging the terms sine t and cosine t separately. Here in this step, we can see that. Then we will compare the coefficients. The coefficient of cosine is 0. Here we can see that there is no term of cosine, so we can write it 0 cosine t. 0 cosine t, right? So this will be equals to 0 and this will be equals to this one, right? 4 over n pi sine t. So you can see that the system of equations, algebraic equations, is generated in the form of a and b. So we can solve this system to find the solution for a and b. Then we will replace in the equation of ap, and then we will generate the final solution for an. So here we are going to use algebraic manipulation. We are solving the two equations by substitution and elimination method. So here we multiply equation 1 by kn squared and then add it to equation 2. So we get this form k square and 4b plus b is equals to 4k n over pi. So from here we can find b. B is common and 1 plus k square, and 4 is equals to 4k n over pi. Then b is equals to this function, right? Then we'll substitute this in equation 2 to find a. So a is equals to this one. Then we will put these values in the particular solution. Here we can see that this is -4 times, because here it was a cosine t, so it's -4 over n5 times this guy times cosine t, and plus here b sine t, therefore 4k n over pi times 1 plus k square and 4. Now we'll apply the initial condition to find C1. For C1, we are going to use the condition we already formulated, that is equals to 0. Therefore, C1 will be equals to this one, right? Because sine of 0 will be, this will be 0 and we applied 0 for t, and this will be cosine t is 1, so this will be -4 over n5 times 1 plus k square and 4. Therefore, we will get C1 is equals to 4 over n pi times 1 plus k square and 4. All right, so now the final solution is generated for an, that is this function. We can put it into the original equation that we called this one the solution of the problem. So we have found a and t. We can replace this a and here with sine and x, and the final solution is generated. So this is the method of eigenfunction expansion. All right, we can formulate the heat equation, especially when there are time dependent sources and time dependent boundary conditions. So this is an easier method to formulate. Now let's move to one more question where the boundary conditions are time dependent. We can see that u of 0 comma t is equals to sine t. Still, these are Dirichlet boundary conditions, but non-homogeneous this time. So the approach is same, but recall that when the boundary conditions are time dependent, so we have to work out for two solutions, and we have to make these boundary conditions homogeneous to solve by using the method of eigenfunction expansion. Therefore, this equation have two parts of solution. One is v of xt plus, then second is w of xt. So for w of xt, we have very simple formula, that is b of t minus a of t over L. These are the boundary conditions, b and a. Here b is equals to 0. This is b and this is a, right? So here we can put b, so 0 minus sine t over L. L is given as L, so plus sine t, then w of xt is equals to sine t times 1 minus x over L, right? Now we are going to work for vt. So now vt minus 2vxx will be equals to ut minus 2uxx minus wt minus 2wxx. This is actually from this equation. V of xt is equals to u of xt minus w of xt. So ut minus 2uxx is given as 0 because it's a homogeneous equation, and then wt minus 2wxx we can find it from this equation. All right, this equation. So we can see that wt will be cosine t times this function, and wxx will be 0 because the maximum power of x is 1, right? So here we can see that wt is this function minus 2 times 0. So now the equation is generated. Vt minus 2vxx is equals to x over L minus 1 times cosine t. The boundary conditions are homogeneous. V0 comma x is equals to 0, Vl comma x is equals to 0, and then for initial condition, Vx of 0 is equals to Ux of 0 minus Wx of 0. So for Wx of 0 will be also 0 because sine 0 is 0, right? and u of x comma 0 is already given as 0. So this is 0. This one is also 0. Therefore, v of x comma 0 is 0. Now we can apply the method of eigenfunction expansion to this static equation, right? So now let's start with fn. Fn is equals to, so the function of xt is this one, right? And fn is equals to 2 over L times this function. Cosine t is treated as constant. So outside the integral, this function is integrated. Here we can see that x over L minus 1 times sine and pi x over L is integrated. And the integral for this function is finally this -2 cosine t over n pi. All right. So we found fn. Now we'll work out for an. So for an, we need initial condition. Initial condition is 0. So work is simple. An will be equals to 0. N of 0, in fact, is equals to 0, right? So now here, this is the differential equation, and boundary condition is 0. So very simple scenario. We will solve this equation similarly as we did in the previous problem. We will use auxiliary equation and the particular solution. Therefore, this is auxiliary equation. From this equation, we found the homogeneous solution. Then for particular solution, we are going to assume a particular solution compatible with the given function on the right hand side, that is of cosine t. Right here we can see that the function is of cosine t. So the particular solution will be a cosine t plus b sine t. We will find a and b in the similar manner. We will generate equations, compare the coefficients by arranging them. Then we will get to algebraic equations, linear equations. We will solve for a and b simultaneously, equation 1 and 2, by elimination method. So here we multiplied 1 by 2n squared pi square over L squared and added to 2. Therefore, we eliminated a and we are only left with b, right? So here we can find b by taking out b as a common. So inside the bracket, we will be left with, this implies that this will be b times 1 plus 4n squared by 4 over L power 4 is equal to -2 over n pi. So we can shift this here and we will get b. Similarly, we will put this one into the equation number 1 and we will find the value of a. So here we did that. A is equals to this function. Now we are very near to the final solution. We only need to find c. For that, we will apply the initial condition. So here is the solution. This is basically an is equals to an homogeneous plus an particular. All right. So an of 0 is 0. So we'll apply the conditions. We will find c. Here we can see that c minus 4 at pi over L squared times 1 plus this function, then c will be equals to this guy. All right, then now just we are going to put the value of c and we have generated our an. Here is the an. We can put this an into the summation that we already know. This is an sine and pi x over L. So an is calculated, wx comma t is calculated. We need to substitute in the equation, and here is the answer: v of xt plus w of xt, right? So hope you guys understand this method. This is a very, very important method. In fact, we just talked about the sine expansion. Now we are going to talk about the Fourier cosine expansion in the next lesson, and then we will talk about the Fourier general Fourier expansion, right? So hope you guys will learn from this. So Goodbye till the next lesson. Thank you for watching the lesson.